Hello and welcome back to my supplemental lectures on linear algebra. In this lecture, I'd like to talk a little bit about the basis of a vector space. You'll recall, hopefully, that the definition of a basis is the following. A collection of vectors, x1 to xn, in a vector space V are said to form a basis of the vector space if and only if they're both linearly independent, okay, and if they form a spanning set for V. So let's just review what these two definitions mean. So linear independence, which I'll just write lazily as Li, this means that a linear combination of these vectors, the x1 through xn, so if we write c1 x1 plus c2 x2, etc., all the way up to cn xn, and we set this equal to the zero vector. So if we set this equal to the zero vector, then linear independence says that the only solution for the unknown, so the only constant c that make this statement true, is if all of the c's are equal to 0. So if c1 equals c2 equals etc., cn equals 0. Okay? And so this is linear independence. Remember, this is the opposite of linear dependence. And linear dependence says that one of these vectors, x1 for example, could be written as a linear combination of the other n minus 1. Okay, so this is the definition of linear independence, but we can think of it as the opposite of linear dependence. To be a spanning set, the criteria, the defining equation is similar, but it's different though, of course. And this says that for any v in the vector space V, so for any element v, we can find coefficients, c1 through cn, such that, so c1 up to cn exist, which make v a linear combination of these basis vectors, what we're going to call the basis vectors, x1 through xn. So they exist such that v can be written as a linear combination. So c1 x1 plus c2 x2, etc., all the way up to cn xn. Okay, and the thing that both of these definitions have in common is the linear combination, right? So the linear independence has a linear combination of the x's adding up to 0, the 0 vector, and then we draw some conclusions about the c's. The spanning set definition has a linear combination adding up to any vector in the space, not just the 0 vector, but any vector, and then we draw some conclusions, basically that we can find such c's to make this work. And so in both cases, we can rewrite these criteria as a matrix product. So we can build a matrix A where the vectors form the column. So if these are vectors in Rn. So we're going to do, so in Rn, we can write these as, this is a matrix of column vectors. So each of these vectors can be written as columns of the matrix A. And then we can form the vector of unknowns, C, C1 down to Cn. And then both of these equations can be written as a matrix equation where the left-hand side looks like A times C. Okay? And so we talked about in class that to determine if our set forms a basis, number one, we have to have the correct number. So again, if we're in Rn, we have to have exactly n of these vectors. So in R3, we need exactly 3 vectors. So that's one thing to check. And once we do that, then the matrix that we build, so as long as that number is correct, so if we have the right number, then this matrix will be a square matrix. And both of these questions, the spanning and linear independence, can be answered by asking, does the inverse of this matrix exist? So we need to determine, does this matrix exist? Okay, and so we're going to do some examples. And see where this leads. So the first example is not an example in R3, but an example in P3. And so to do this one, we were given these 3 polynomials in P3. To do this one, we want to use the result from chapter 1, I guess it would be, it's section 3.1, where we can identify the space P3 of polynomials with the space R3 of vertical vectors. And so remember that the identification goes like this. We first write out all the missing terms, so 2x squared plus 0x minus 1. And then we take the coefficients, and then this has got to be written in the descending order, this is our convention. And then we can pluck out these coefficients and write this as a vertical vector, 2, 0, negative 1. The vector 3x plus 5, again rearranged, is 0x squared plus 3x plus 5. And that can be converted into the vertical vector 0, 3, 5. And then finally, this vector x minus 3x squared, this one we have to rearrange and write as negative 3x squared plus 1x plus 0. And so as a vertical vector, this will be minus 3, 1, 0. Okay? And now we can collect these vertical vectors all together to build the matrix. And it's going to be, we're going to be able to take the determinant of this matrix and get the answer. The answer will correspond to these functions in P3. So 2, 0, 1, negative 1, sorry, 0, 3, 5, negative 3, 1, 0. All right, and now we just have to compute the determinant of this matrix. So as we know, we can expand this matrix on any row or column. Each row and each column has 1, 0, so it doesn't really matter. So we'll just expand on, I'll expand on column 1, or sorry, row 1. And so the determinant of this matrix A is going to be equal to, give myself some more room here. The determinant of this matrix A is going to be equal to 2 times times the determinant of the minor, so times 3, 1, 5, 0, minus 0 times the determinant of who cares, because it's going to be 0, and then plus negative 3, so minus 3 times the determinant of this minor. And so now we just compute. We have 2 times, so this will be 0 minus 5 plus 0, and then minus 3 times, this will be positive 3, 0 plus 0 minus negative 3. So positive 3. And so this is negative 10 minus 9, which is negative 19. And this number, this is the determinant of the matrix A. This number is not 0. And since this number is not 0, it means that the columns are all linearly independent and they span R3. But those columns came from the polynomials over here. So our conclusion then is that these polynomials are linearly independent in P3, and they span all of P3. So they do form a basis for P3. Okay, we just have to check both criteria, and in this case, checking both criteria just comes in the form of taking one determinant. Okay? Here's another example. This one says to find a basis, so find a spanning set of linearly independent vectors. That's what we're charged with finding here. Find a basis for the subspace of our 2x2 matrices consisting of all the skew symmetric matrices. So we have to first remember what it means to be skew symmetric. Okay, so skew symmetry says that our matrices have to satisfy A transpose equals minus A, negative A. Okay, and so let's think about what this forces our matrices, which are now our vectors in our vector space, but what this forces these matrices to look like. So let's start with a generic matrix A in this space of 2x2 matrices, so we can call it A, B, C, D. And then we can do these two operations to it. So A transpose is going to be the matrix AC, B, D. You just turn the first row into the first column into the first row and vice versa, and the second column into the second row. And then negative A is just going to be the original matrix A over here, but with all negative entries. Okay, and for the matrix to be skew symmetric, we have to set these two things equal to each other. And we're, again, for that to work in a matrix, then we have to do it component by component. So we set all these components equal to each other, and we solve for the, see if we have any criteria on these entries. So first of all, we have A has to equal minus A. So that forces A to be 0. The only number that satisfies this is 0. And the same thing is going to be true of D. So D has to equal minus D. That forces the diagonal element D to be 0. And then both of these off-diagonal equations say that B and C have to be the same but with opposite sign, right? So C should equal minus B, and B should equal minus C. Okay, and so this forces our matrices in this subspace of skew symmetric matrices. This forces our space to be of this form. So it's all the matrices that look like 0, B, minus B, 0, for some B in R. Okay, so just by writing this, now we have an idea of what this space should look like. So how do we build all these matrices? Well, all of them have the similar form, and they only have one free variable. B is the only free variable in this scenario. Even though it comes from a space that had 4 free variables to start with, this criteria cuts down a lot of possibilities on what these matrices can look like. Okay, and so every matrix in this space S, so let's call this one capital B, every matrix in this space looks like some number B times the matrix 0, 1, negative 1, 0. Okay, and so we could write then that this space S is equal to the span of this matrix, right? So it's equal to the span of all the matrices, all linear combinations of this one matrix. Now, how do you take linear combinations of a single matrix? Well, you just multiply by every real number. And so this right here, this set, this one single matrix, this forms a basis for the space of 2 by 2 skew symmetric matrices. Okay, so this is our answer. So the answer, so to find the basis, the answer is this set. Okay, so I'll write it over here. The basis is then just the collection of that one matrix. Okay, and now this is not the only answer. We could multiply this by any number we choose. So we could have 0, 2, negative 2, 0, or even 0, negative 1, 1, 0. That's fine. So there's lots of different answers, but this one is an answer. It's good enough. Okay, and so that concludes this session, and I look forward to seeing you next time.